Name of the subject Control System Engineering, Chapter Control System Components. 6 Mr. Electrical. Faculty represents Arun Ranjan Naik, HOD Electrical Engineering. Controller components. They can be classified in three kinds. First one sensor, second one differentiation and amplification, third is actuator. First comes to the sensor. The low power transducers, control variable employed for position, velocity measurement, etc. Number 2, differentiation and amplifications. To get error signal and amplification to suitable level. Next, operation amplifier is used for differentiating input and feedback signals. Third one is SCR is used for different power stages. Third, actuators. It is a device whose output is mechanical motion. It performs variety of tasks to manipulate the control process or plant. For example, open or close a valve in a plant. Actuators are classified as actuators, pneumatic actuators, electric actuators, hydraulic actuators. The electric actuators have inherent flexibility in electrical power transmission and have linear speed torque characteristics which is desired. Hence, among all the actuators, electric actuators are widely used. For low speed and high torque applications, hydraulic actuators are generally used. Electric actuators. Electric actuators are again of three types: DC motors, AC motors, stepper motors. In lower power ratings, these are called as servo motors. DC motors are costlier than AC motors. This is because of additional cost of communication gear. DC motor have linearity of characteristics, higher stall torque inertia ratio. Higher torque inertia ratio indicates dynamic response of the motor. Electric actuators for stepped motion are known as stepper motor. Next come to servo motor. These are AC or DC. Servo motors, the commonly used power devices in electrical control systems, are AC and DC servo motors. The AC servo motors are ideally suitable for low power applications. They are rugged, light in weight, and have no brush contact. AC servo motors. It is basically two-phase induction motor. This is the main winding, this is the rotor winding, this is the control winding. The starter windings are oriented 90 degrees apart. Hence, this results into magnetic field of constant magnitude rotating at synchronous speed. Torque speed characteristics. This is the curve drawn between torque versus speed. The speed represents in x-axis and torque represents in y-axis. This is the line for small x by r. This is the line for curve for large x by r. This is the point start from A and B, where rotor reactance is X and rotor resistance is R. X-R ratio is generally high to obtain maximum starting torque, stable operation, and to get linear torque speed characteristics. The servo motor characteristics. This is speed torque curve. This is E0, E1, E2, E3, where E3 is greater than E2, is greater than E1, is greater than E0, is equal to 0. And this one is the line for speed versus torque. This is TM is the stall, E is a rated value, this is E0 is the no load voltage, and this is the line here. Note the in low speed region the curve are nearly linear and equidistant. It rebels. Slope of torque speed characteristics reduces as control voltage phase voltage decreases. The torque speed slope in a low speed region is nearly one half of the slope at rated voltage. Approximations. The curves are approximated to linear characteristics. This approximation is valid as motor rarely operates at higher speeds. The torque is proportional to applied voltage. Since the speed torque curves are assumed linear and proportional to applied voltage. These curves are equal spaced. The motor torque Tm is given by Tm is equal to Ktme plus m d theta dt. This is servo motor, this is actuating signal, this is control phase, this is rotor, this is reference phase, this is Tm, this is theta, this is Jb, where E is the control voltage, d theta by dt is the speed. Its Laplace is Tm of s is equal to Kmes minus ms theta s. The load has J and B components. TL is equal to J square plus Bs. As motor drives the load, Tm is equal to Tm minus TL, Kmes minus ms theta s minus is equal to J square plus Bs theta s. To get theta s by s in the objective, Knes is equal to J a square plus Bs plus ms theta s. Theta s by s is equal to Ktm by Js B plus m whole into s is equal to Ktm by s whole into b plus m whole into 1 plus Js by b plus m. Put Km is equal to Ktm by b plus m and tau m is equal to Jm by b plus m. Theta s by es is equal to Km by 1 plus s Tm. The SFG is easily given from the following arrangement. Theta s by es is equal to Ktm by j square plus b plus m into s whole into Ktm by j square divided 1 minus m plus b by js. It has one forward path of gain Ktm by j square and loop gain m plus b by js shown in the figure. The term m contributes to negative slope. This improves friction and improves stability. It is called internal damping of two-phase AC motors. The characteristics are easily determined by two set tests. See figure 1 below. First one is block rotor test, speed 0, and no load test, torque 0, load torque 0. This is the ES versus theta s. This is the line for s theta s. This is s square theta s. This is the path for 1 by s. This is the path for 1 by s. This is the feedback path minus m minus b by j Ktm by j. So this is the diagram permanent magnet DC motor, PM DC motor, speed torque curve. This is the line for speed. This is the line for torque. So this is no load speed. This one is the block rotor torque. Ktm is equal to block rotor torque or rated voltage by rated control voltage. M is equal to block rotor torque or rated voltage by no load speed. DC servo motors. These are constructed with